All right, let's jump right in. Today we are diving deep into the brain, and I am seriously so thrilled you're here. We are going to unpack the biological realities, the really dense molecular mechanisms, and the profound ethical dilemmas surrounding cognitive enhancers. Whether you call them nootropics, study aids, or smart drugs, you know the pursuit of an upgraded brain is literally everywhere these far days. But what is actually happening under the hood? Well, let's find out in today's explainer.
It's kind of the ultimate modern question, isn't it? Do smart drugs actually make you smarter? Like, if you pop a prescription stimulant right before a massive exam or a major project, are you genuinely increasing your raw fluid intelligence? Or, and this is a completely fascinating possibility, are you just creating a hyper-focused, super energetic illusion of productivity? To answer that, we really have to cut through the hype and look directly at the data.
So, here is our roadmap for the explainer. We're going to start with the smart drug paradox, map out a taxonomy of cognitive enhancers, and then look at the actual performance trade-off. After that, we'll drill all the way down into the cellular biology of brain upgrades, explore the industry's shift to resilience, and finally, zoom back out to tackle the ethics of enhancement. Lots to cover.
Okay, let's dive into this first part. Section 1. The smart drug paradox. You know, historically, neurology has had a super clear mandate: heal the sick. But today we're seeing this massive paradigm shift. The focus is actually moving away from just treating pathological deficits, like Alzheimer's or ADHD, and moving toward optimizing and upgrading the completely healthy human brain.
And this shift introduces a really fascinating concept called cosmetic psychopharmacology. Think about it. Just like cosmetic surgery alters a perfectly healthy body, cosmetic psychopharmacology uses these compounds to tweak and improve normal cognitive variation. And honestly, this fundamentally blurs the lines. When exactly does a necessary medical therapy end and an artificial enhancement begin? Because cognitive capacities exist on this huge spectrum. Enhancing someone with naturally poor memory might just bring them up to a normal baseline. It is a very, very tricky boundary to define.
Moving right along to Section 2. Taxonomy of cognitive enhancers. To truly wrap our heads around this landscape, we first have to realize that smart drugs are absolutely not a monolith. They do wildly different things to your brain chemistry. So let's break down the diverse taxonomy of these compounds.
We basically have 4 distinct categories here. Up at the top, prescription stimulants. Things like methylphenidate and modafinil. These act on dopamine and noradrenaline reuptake, and they give an immediate, super noticeable jolt to your system. But contrast that with classical nootropics, which modulate AMPA receptors, or cholinergics, which synthesize acetylcholine, or botanicals, which use antioxidant pathways. Those bottom 3 categories? They don't give you a sudden, buzzy rush. Instead, they require consistent dosing to build slow, structural neuroplasticity and metabolic support in the brain. They're playing a long game, whereas stimulants are playing a very short one.
Which perfectly sets up Section 3, the performance trade-off. So, what actually happens when a healthy person takes prescription stimulants to try and get ahead? Does that short game actually work for complex tasks? And this brilliantly illustrates a massive gap between feeling smart and actually acting smart. On one hand, you've got the perceived effect. You feel incredibly motivated, your fatigue completely vanishes, and you execute physical tasks faster. You literally feel limitless. But then, look at the actual output when faced with complex computational problems. The data shows a decrease in optimization efficacy, a total loss of strategic structure, and systemic performance reversals. Researchers proved this using something called the knapsack optimization task. It's basically a complex problem requiring users to maximize the value of items in a virtual knapsack. Under stimulants, participants actually spent more overall time and made way more moves. Their move velocity was lightning fast, sure, but their patterns devolved into completely random, non-systematic guessing. Because stimulants artificially spike your baseline reward salience so much, users abandon careful multi-step planning for rapid, uncoordinated attempts. The crazy result? Above-average performers actually saw a sharp drop in their productivity, while only below-average baseline performers saw slight relative increases.
So the reality? It's honestly quite modest. When you look at massive meta-analysis of drugs like modafinil and methylphenidate, they show tiny effect sizes, only 0.12 to 0.21 in healthy adults. These drugs absolutely do not produce a generalized increase in fluid intelligence. And this is largely due to what's called an inverted U-curve dependency. If you already have an optimal baseline of dopamine in high performance, pushing more stimulation into the system actually pushes you right off the peak and impairs your cognitive flexibility.
Let's move to Section 4 and see how this builds into the biology of brain upgrades. Because if stimulants don't make us fundamentally smarter, what does actual, long-term memory formation look like at the cellular level?
Well, true cognitive enhancement relies on a process called long-term potentiation, or LTP. This is the persistent strengthening of your synapses. And the undisputed superstar of this entire process is the AMPA receptor, which mediates over 90% of rapid excitatory transmission in glutamatergic neurons. True intelligence and lasting memory rely on the structural localization and function of these specific AMPA receptors, not just temporarily flooding your whole brain with dopamine.
Let's actually trace the incredibly dense molecular journey of an AMPA receptor. Step 1 is synthesis. They're assembled right in the endoplasmic reticulum. Step 2 is transit. Think of the actin cytoskeleton in your cells as a microscopic transit system. A motor protein called myosin VB acts as the engine, propelling vesicles carrying these AMPA receptors right along the actin tracks. Finally, step 3 is anchoring. A transmembrane protein called stargazing essentially acts as the synaptic stop sign. It binds to a scaffolding protein called PSD95 to firmly stabilize the AMPA receptor right at the postsynaptic membrane. This incredibly precise physical journey is exactly how memories are built.
When we look at how different compounds interact with this biology, the contrast is kind of mind-blowing. Classical pyrrolidine class nootropics, like piracetam, actually bind to the dimer interface of AMPA receptors, slowing their desensitization, and they restore mitochondrial membrane fluidity. They literally work with the biology. Stimulants, on the other hand, just force immediate neurotransmitter release. This risks severe overstimulation, dependency, and in young adults, it can actually disrupt the natural synaptic pruning necessary for a healthy brain.
Okay, Section 5, the shift to resilience. Because of those hard biological limits we just talked about and the high-risk, fatiguing nature of chronic stimulant use, the brain health industry is actively pivoting. We are entering an era focused on long-term cognitive resilience.
A major focus of this pivot is BDNF, or brain-derived neurotrophic factor. This is a master regulator of neuroplasticity. But here's the catch, and it's a big one. Its precursor, pro-BDNF, actually promotes synaptic depression and cell death. It's only the mature BDNF binding to specific receptors that promotes beautiful dendritic growth and long-term memory. And crucially, BDNF's positive effects depend strictly on localized, activity-dependent release in the brain. You can't just artificially flood the whole system and expect to get permanently smarter. The brain requires targeted, holistic support.
That's exactly why the next generation of nootropics is shifting away from short-term alertness toward lifelong cognitive resilience. We're seeing ingredients like citicoline, which actually enhances the structural integrity of neuronal membranes. We're seeing botanicals like lion's mane mushroom, which supports that vital neurotrophic signaling we just talked about. The entire goal now is avoiding overstimulation and adrenal fatigue entirely. Ultimately, science is basically saying, hey, you cannot biohack your way out of bad habits. Restorative sleep and effective stress regulation are the fundamental bedrock of memory consolidation.
All right, let's zoom all the way out for Section 6, the ethics of enhancement. We've looked at the microscopic level, now let's look at the society we are building. The profound socio-ethical debate surrounding these compounds in our schools and workplaces simply cannot be ignored.
The source material brings up this really stark quote regarding the use of prescription stimulants in competitive universities. The white version of cheating. It's a heavy thought, right? We're impartially presenting this to illustrate a massive socioeconomic disparity. Students from underrepresented or lower-income backgrounds correctly point out that access to doctors, ADHD diagnoses, and prescription stimulants is a privilege unequally distributed across society. When pharmacological enhancement requires money and access, it genuinely risks turning existing economic advantages into biological advantages.
So, the crucial point is really how we as a society define achievement. We are currently staring down two entirely competing philosophical models. The accomplishment argument basically states that achievements made using enhancers are less authentic, they just don't reflect an individual's true unassisted capability. Conversely, the collaborative authorship model argues for an open enhancement culture where the final output, say a brilliant piece of code or a groundbreaking research paper, is prioritized over the individual's unassisted struggle. We definitely aren't here to say which side is right, but it is entirely up to us to weigh the merits of individual effort against optimized collective output.
And this puts institutional policymakers in a really tough spot. They've basically got three options. They can promote research into healthy enhancement to dispel myths and create informed policy, though this might divert funds from sick patients. They can take a neutral stance, but that leaves everyday consumers completely without any safety guidance. Or they can prevent research to avoid normalizing drug use, but history shows us that prohibition often just creates highly unregulated, dangerous black markets.
Which brings us to one final really provocative thought to end this explainer. As the science of cognitive enhancement continues to evolve from cellular biology all the way up to societal ethics, we have to ask ourselves, are we truly optimizing our brains to live richer, fuller lives, or are we just medicating ourselves to keep up with the demands of an increasingly exhausted world? It's definitely a question we will all have to answer eventually. Thank you so much for exploring this fascinating topic with me today. Keep learning, keep questioning, and I'll catch you in the next explainer.